All right, so hi everybody, welcome back. What we're going to be doing today is finishing up chapter 20. So by the end of this video, we'll be all done with the material from chapter 20 that we need to cover. And the first thing we'll start with is an example problem. So here we have a 67.5 gram ice cube, initially at 0 degrees Celsius, which is placed in a room where the temperature is 22 degrees Celsius. After a few minutes, the ice cube totally melts, and the now liquid water has the same temperature as the room, which is 22 degrees Celsius. The room is very large, so its temperature is not significantly changed as the ice cube melts. The room is also well insulated, so no heat flows in or out of the room. The latent heat of fusion of water is 333,500 joules per kilogram, and the specific heat of liquid water is 4,186 joules per kilogram per Kelvin. So the question is, what is the total entropy change of the ice cube in this process? What is the total entropy change of the room in this process? And then what is the total entropy change of the universe in this process? And then after you answer those questions, do we have a reversible, irreversible, or an impossible process based on your calculations? So what I'd like you to do is pause the video, see if you can try to work this out, and then we'll go through it together. Okay, so we'll start by calculating the entropy change of the ice cube. And we'll call that the system. So the system is just the ice cube. The environment would be the room around it. And we'll remember that a change in entropy, delta S, is given by the integral dq divided by t. This is the Clausius definition of entropy. And we have two different things we need to think about when it comes to the ice cube. So for one, the ice cube is going to melt, so there's going to be a phase change. And we learned that the heat during a phase change is given by plus or minus m times L, where m is the mass that's undergoing the phase change, and L is the latent heat. Okay, so if we have a phase change, we also will remember that phase changes happen at constant temperature. So if we calculate delta S for the melting of the ice cube, we're going to have 1 over T, we can pull out the temperature because that's constant, times the integral dq. And when we integrate dq, we just get the total heat for the process of melting, and we're dividing that by the temperature. So in particular, let's say this is Q melt divided by T melt, the temperature at which ice melts. And the heat on top of this is plus m times LF. We're choosing the positive sign because heat has to flow into the ice cube in order to melt it, so it will be positive. And we'll divide by the melting point of ice. Now, that's not the only thing that happens to the ice cube. The ice cube, after melting, is now liquid water at 0 degrees Celsius. But that now liquid water is going to heat up, its temperature is going to increase until it reaches the temperature of the room. So we also have a temperature change that's going on here. And we'll remember that in that case, Q is given by mc delta T. If we want to express this in differential form, in other words, dq is equal to mc times dt. That's how we do it. So then delta S for the temperature change would be given by the integral of mc times dt over t. Okay? Because, again, dq is mc times dt, as we just said. And we can pull out the constants mc. So the mass and the specific heat will be constant. So then we're left with dt divided by t. The temperature is not constant. It's going up in this process, so we can't pull that out. But the limits will be some kind of t initial to some kind of t final. Okay, so I'm going to skip a little bit of the details here because, again, we've seen this type of integral a lot. 1 over t integrates to the natural log of t. So we'll have mc times the natural log. And when we evaluate at the limits, we can write this as t final over t initial. And of course, the entropy change for the system would be the entropy change that the ice cube undergoes as it melts, plus the entropy change as its temperature goes up to be in equilibrium with the room. So what we have here is m times the latent heat of fusion divided by the melting point, which is where we start, so T melt, plus mass times specific heat of water times natural log T final over T initial as it heats up to the temperature of the room. Okay, so before we make any calculations, we need to get all our temperatures in Kelvin. So temps must be in Kelvin. So the melting point of ice is 0 degrees Celsius, but we'll add 273 to give us 273 Kelvin. The initial temperature of that now liquid water is, well, T melt, right? Which is 273 K. But then the final temperature after it warms up to match the temperature of the room, that's 22 degrees Celsius plus 273 gives us 295 K. So therefore, the entropy change of our system is going to be mass, which is 67.5 10 to the minus 3 kilograms, times latent heat, which if we write it in scientific notation is 3.335 10 to the 5 joules per kilogram Kelvin. And then we'll divide that, that unit is joules per kilogram, because we're talking about a latent heat. And then we'll divide that by 273 K. Okay, cancel out kilograms. We'll see the units work out to joules per Kelvin. But we have to then add to that the mass, 67.5, 10 to the minus 3 kilograms. Now times C, which is the specific heat of the liquid water, 4,186 joules per kilogram Kelvin, times the natural log of T final, which is 295 K, over T initial, which is 273 K. And again, kilograms cancel, we get units of joules per Kelvin. So this first term, if you calculate that, is about 82.458, round to 3 sig figs joules per Kelvin. The second term over here, if you calculate this, is 23.808. I want to keep 3 sig figs on that. Joules per Kelvin. Remember that when you add two numbers, the rule is you round to the smallest number of decimal places. So we're going to round to 1 decimal place. In other words, we'll have 106.266 before rounding, but we'll round off to that first decimal place, joules per Kelvin, which gives us 106.3 joules per Kelvin, something positive, by the way. Okay, so that's the entropy change of the ice cube as it melts and then reaches the same temperature as the room. Now let's look at the entropy change of the environment. Which for our purposes we can just think of as the room. Okay, so delta S for the environment is going to be given by the same integral of dq over t, but we're applying this specifically to the room now, not the ice cube. So the room has a constant temperature. In other words, the temperature of the room since it is so big, is not really significantly affected by the ice cube melting. So we'll say the room has a constant temperature, which means we can pull it out. So we have 1 over T out front times integral dq, which when we integrate dq is just q divided by T. Let's be a little more specific. Q would represent the heat flowing into or out of the room, so we'll call it Q room. The temperature would be the temperature of the room, which again is constant. So let's just note that the room maintains a constant temperature. T room equals 22 degrees Celsius or 295 Kelvin. Okay, so here's what we need to do next. We need to realize that any heat gained by the ice is lost from the room. So let's see how we can know that that's the case. The total heat for the room plus the ice cube, so Q room plus Q ice, since this is an insulated system, okay, that's going to equal 0. So therefore, Q room is equal to minus Q ice. That's what I mean when I say any heat gained by the ice is lost from the room. There's just a relative negative sign between them. So what is Q ice? Well, we can figure it out. We have the minus sign up front, of course. So the ice, again, has to gain M times LF to melt. Okay, it has to take in that latent heat. And then an additional MC delta T to get to the final temperature. So that's what we would need to calculate to get Q room. Okay, so Q room then is equal to minus the mass of the ice is 67.5 10 to the minus 3 kilograms. The latent heat is 3.335 10 to the 5 joules per kilogram. And then MC delta T is 67.5 10 to the minus 3 kilograms for the mass. Now we have liquid water, so the specific heat is 4,186 after melting joules per kilogram Kelvin. And what's delta T? Well, basically, the temperature increases by 22 Kelvin. The temperature of the ice cube goes up by 22 Kelvin as it goes from the melting point to the temperature of the room. So if we look at the units, kilograms cancel in the first term, kilograms and units of Kelvin cancel in the second term, giving us just a heat measured in joules. And if you calculate that heat, you'll find that it comes out to minus 2.873 10 to the 4 joules. So again, Q for the room is negative, indicating the room is losing some heat and giving that heat to the ice cube. Okay? And so, what did we say earlier? The temperature change, delta S for the environment, is simply, let me write it again, Q room divided by T room. So Q room is minus 2.873 10 to the 4 joules. And of course, when we divide out the temperature, when we calculate an entropy change, that must be in Kelvin. So remember, the temperature of the room is 295 K. And if you do that calculation, you're going to find that it comes out to minus 97.389. Keep 3 sig figs on that, joules per Kelvin. Okay, so let's do the entropy change of the universe. So for the universe as a whole, delta S is the entropy change of the system plus the entropy change of the environment, which again, the system is the ice cube and the environment is the room in this problem. And so we had 106.266 rounded to the first decimal place, joules per Kelvin for delta S system. And then we have minus 97.389 rounded to the first decimal place, joules per Kelvin for the entropy change of the environment. So this works out to positive 8.877, round to the first decimal place, joules per Kelvin, which is about 8.9 joules per Kelvin, and that is something positive. So since this process increases the entropy of the universe, in other words, delta S for the universe is positive, we know it's irreversible. Which makes sense, by the way. If you put this ice cube out into this room where the temperature of the room is above the melting point of the ice cube, it's going to melt, it's going to become a puddle of water, and at no point are you going to see that puddle of water reassemble itself into an ice cube. It's not going to be reversible. Okay, and this finally brings us to the second law of thermodynamics. So before we state what the second law is, let's just remind ourselves what the first law says. The first law says that the total energy of the universe is conserved. So the first law is a conservation of energy statement. The second law says that the total entropy of the universe always increases over time. It doesn't decrease. So the second law has kind of a different character. The first law is about a quantity called energy, which is conserved and it stays the same. The second law is about a quantity called entropy, which is not conserved in any way. In fact, it's always going up. The entropy is always increasing for the universe as a whole. Okay, so let's get a little bit more into the specifics here, okay? You can certainly have a system that you're looking at where the entropy of that system is decreasing. But the only way that can happen is if the entropy of the environment around it is increasing by at least the same amount. Okay, so in other words, you can decrease entropy in one place, but only if you increase the entropy in another place by at least as much. So when we look at the total entropy change of the universe for that process, it's always going to be positive, it's always going to be going up. So here's an example, okay? Let's say you have a cup of marbles and you just drop them all over the floor and let them scatter around the room, okay? Then you take those marbles and then you put them back into the cup, okay? So when you take those marbles that are scattered all over the room and you pick them up and you put them into a cup, that does decrease the entropy of the marbles so that there's less disorder in those marbles than there was before when you put them back into the cup. But the thing is, by putting the marbles back into the cup and picking them up and moving them, you are doing work. You're actually doing mechanical work to move those marbles. And in doing that work, you're giving off some heat to your environment. That is going to lead to an entropy increase overall. Okay, so even if you decrease the entropy of the marbles, the only way you can do that is by increasing entropy somewhere else. That's really what the second law has to say. And so now that we understand the second law and what it says, we can go back to heat engines, which was sort of the starting point of this whole lecture. And remember, a really big result of this lecture as a whole is that a perfect heat engine with 100% efficiency, and it doesn't give off any waste heat, is impossible. Okay, that's not something you can have. It would violate the second law of thermodynamics. So remember our schematic for a heat engine, where you have a hot reservoir and some heat flows from the hot reservoir into your working substance, into your gas, and we call that heat QH. There might also be some heat flowing into the cold reservoir from your gas, and we call that QL. And also, we want the engine to be doing some work, so that's W. Okay, this is a schematic of an impossible heat engine where it takes in some QH, it does some work that is equal to QH, so all the heat that comes in is somehow converted to work, and none of it becomes waste heat. This is not possible. Okay, and the reason that's not possible can be understood in terms of the second law. Okay, so we have heat and work. Okay, when heat flows into a system, the energy that's added to our gas is highly disordered. Okay, it's the energy of randomly moving molecules that are bumping into each other, bumping into the walls of the container. This is a high entropy form that the energy can take on because it's highly disordered. Okay? Now, when work is being done on a system, that energy that's added is highly ordered. So, for instance, if you have a work being done on a spinning wheel to make it rotate, instead of the molecules randomly moving around like what we have here, the molecules are moving in an organized fashion. They're all just moving in a circle like this. So this is low entropy, highly ordered motion. This is high entropy, very disordered motion. And if we're imagining that the heat engine is just taking in heat and converting it all to work, well, that's like saying you're going from highly disordered to ordered. That's like saying you're decreasing the total entropy of the universe, which again is a violation of the second law of thermodynamics. So the second law, now that we've seen it, explains where we started off in this lecture, which is that perfect heat engines that are 100% efficient, don't give off any waste heat, are impossible because they violate the second law of thermodynamics. Okay, so the next thing I want to get into, and we'll really only touch on this in kind of a conceptual way, is something called statistical mechanics. You can kind of think of this as the next level of thermodynamics. If you were taking, let's say, upper division physics in a university class, you might see statistical mechanics at some point. So I do want to touch on it a little bit just so you have some appreciation for it. So statistical mechanics, also known as stat-mech, is a branch of physics that uses probability and statistics to explain thermodynamics. Okay, so to explain things like heat and temperature in large systems. And this is the more modern view of thermodynamics. So everything we've learned up to this point, roughly speaking, is stuff that was worked out by the mid-1800s. Then if you go a little past that, past the mid-1800s, the way people do thermodynamics is stat-mech. Okay, this is the modern conception of thermodynamics. Okay, so there are two definitions that I'd like to nail down before we go any further, and that is the definition of a microstate and a macrostate. So a microstate is basically what your system looks like on a microscopic level. And of course, we know that something like a gas or anything really is just a collection of atoms and molecules at a microscopic level. So if we want to know the microstate of the system, then we need a description of the position of every single particle and the velocity of every single particle in the system. So this is a lot of information, right? We might have like 10 to the 24 different molecules, and for each one, we need to know the position x and the velocity v. So this is a huge list of positions and velocities for all the particles. That's what would constitute a microstate. So a macrostate is just the opposite. It's what the system looks like on the large scale. It's defined by the large scale properties that we can actually measure. We'd never know the microstate of a system. We'd never know the exact position and velocity of every molecule of gas in the room, let's say. But you could know the macrostate. You could know things like the temperature, the pressure, the volume, and the number of particles. Okay, so that's the difference. The microstate is exactly what's going on to each particle. How fast is it moving? Where is it located? A macrostate is a bit more of a general description. Just we want to know the temperature, pressure, volume, things that we can actually see on the large scale. All right, so next I'd like to show you an analogy that's really helpful for thinking about the difference between microstates and macrostates. So in this analogy that I'm going to give you, I want you to think about a series of 4 coin flips. So we take a coin, we flip it 4 times in a row, and we just observe what happens in those 4 coin flips. We can consider the number of times that heads came up to be the macrostate, while if we look at the exact outcome of each and every single flip, that will be the microstate. So the macrostate is just how many times did heads come up. The microstate is exactly what happened in each of the 4 flips. So what I want to do here is consider all the possible ways that you can flip a coin 4 times. What are the possible outcomes that you could get? Okay, so if you flip a coin 4 times, one way this could go is you can get 4 heads, 0 tails. There's actually only one way this can happen. If we write H, 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 that means on the first flip, we got heads. The second flip, we got heads. The third flip, heads. Fourth flip, heads. That's the only way this can happen. So what we say is there's one microstate that comes out this way. But now, if we think about 3 heads and then 1 tails, there's actually more than one way you can get this, because you can get tails on the first flip and then 3 heads after that. Or you can get tails on the second flip, so that would be heads, tails, heads, heads. You get on the third flip, which is heads, heads, tails, heads, or on the fourth flip, so heads, 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 tails. So there are 4 different ways this can happen. So we say these are the 4 microstates that correspond to 3 heads and 1 tails. Okay, what about getting an even split, 2 heads, 2 tails? There are even more ways this can happen. Okay, you can get 2 tails, and then the next 2 flips you get heads, or just flip that around. The first 2 flips you get heads, and the second 2 you get tails. Okay, you could get an alternating sequence where it's heads, tails. You could have an alternating sequence, but it starts on tails, so tails, heads, tails, heads. Or you can get one that looks like this. Tails, heads, heads, and then tails. Or you can get heads, tails, tails, heads. Okay, so these are the different ways you can flip a coin 4 times, and in total you get 2 heads, 2 tails. So what we say is there's 6 microstates that look like this. Okay, what about 1 heads and 3 tails? Well, that's kind of similar to what we saw before. If you only get heads once, it could happen on the first flip followed by 3 tails, or it can happen on the second flip, so tails, heads, tails, tails. It could happen on the third flip, so tails, tails, heads, tails. Or it could happen on the last flip, so you get tails, 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 heads. Okay, as far as 0 heads and 4 tails, there's only one way that can happen, which is just tails, 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 tails. So there's 1 microstate here. And then I forgot to write that there are 4 microstates over here where you get 1 heads, 3 tails, okay? So that's the sort of thing I want you to think about, okay? So if we fill in this table, these are all the different possibilities we wrote out. Again, 4 heads, 0 tails. There's only one way that can happen. 3 heads, 1 tails. We have these 4 possibilities. 2 heads, 2 tails. We have these 6 possibilities, and so on. And actually, if we count all the possibilities, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So if you flip a coin 4 times, there's 16 possible ways that can happen. Now, we saw earlier that the number of microstates for the first case is 1, and then 4, and then 6, and then 4, and then 1. We already worked that out. And if you count all those up, you get, again, 16. So there's 16 ways that can happen. So if we want to know the probability of each of these cases, like what's the probability I flip a coin 4 times, and every single time it comes up heads. Well, this is how you should think about that. There's only one possible microstate that comes out this way, out of a total of 16, and they're all pretty much equally likely. It's not like this combination is more likely than that. They're all pretty much on the same footing. So the probability should just be 1 divided by 16. Okay, it's a 1 in 16 probability for it to come out this way. And by the same token, to come out as 3 heads, 1 tails, that should be 4 over 16, because there are 4 ways it can come out that way out of a total of 16. So 1/4 would be the probability. For 2 heads, 2 tails, there's 6 ways we can get that out of a total of 16. So 6 out of 16 is the same as 3 out of 8. So that's the probability there. And then 1 heads, 3 tails is probability of 1/4. 0 heads, 4 tails is a probability of 1/16. So we kind of know intuitively that the most likely thing to happen is you get 2 heads, 2 tails, and it's less likely that you just get a string of all heads or all tails. But this is why. This is how we can actually calculate that this is the most probable thing that can happen. Okay, so what does this all have to do with entropy, which is, of course, the main topic of this lecture? Well, let's get into that. Remember that in statistical mechanics, a microstate is a description of where every single particle in your system is and what its velocity is. So it's really detailed information about what every single particle is doing, right? So the assumption in stat-mech, it's one of the kind of fundamental assumptions in stat-mech, is that all possible microstates are equally probable. Okay, it's not like some are favored over others, they're all just equally probable. But the thing is, there's often many different ways that you can take a system and rearrange it, and it still looks the same on the large scale. In other words, there are many different microstates that can correspond to the same macrostate. Let me show you an example of this. Well, actually, if we go back to the coin flips, right, we saw there are 6 different ways you can get 2 heads, 2 tails, right? So there are many different ways you can get that macrostate. In the case of, let's say, a box of gas, we can imagine that we have some molecules configured like this, but if we just sort of switch 2 of them out of this huge number of molecules, it looks the same on the large scale, right? If you took the air in the room and you just switched 2 of the molecules, you wouldn't notice that. It would have no measurable effect on the temperature or the pressure or anything like that. You'd be in the same macro state, but technically you'd be in a different microstate because you've rearranged 2 of the molecules, okay? And if you have a large number of molecules, there's a ton of different ways you can rearrange things, switch molecules around and so on, so that it still looks the same on the large scale, okay? So, okay, we can count the number of different microstates that correspond to a given macrostate. That's something we can always do. And we can also count the total number of possible microstates. If we take that ratio, that's the probability of finding our system in a given macrostate. So we call n the total number of possible microstates. We call w the number of microstates that correspond to a given macrostate. So to go back to the coin flip example, one of the macrostates was you get 2 heads, 2 tails. Okay? How many different ways are there to get that macrostate? There were 6. So that would be w for getting 2 heads, 2 tails. But n would be the total number of possibilities, which would be 16. So what we did is we took 6 over 16, which works out to 3 over 8. And we said the probability of getting 2 heads, 2 tails is 3 over 8. So that same kind of logic applies to statistical mechanics when we're looking at, large numbers of particles, okay? So the way we define entropy in stat-mech is given by this equation. And this is an equation that was developed by this guy over here, Ludwig von Boltzmann, in about 1875. And this is a really important equation. And in fact, you'll see this equation on Boltzmann's tombstone. Okay, so where he's buried, this equation is written on his tombstone. And the equation says S is equal to KB times the natural log of W. Okay, so what's S? That's the entropy. What's KB? That's Boltzmann's constant, equal to 1.38 times 10 to the minus 23 joules per Kelvin. And what's W? Remember, that's the number of microstates that correspond to a given macrostate. So this is telling us how to calculate the entropy of a system that has a certain macrostate. So KB is a constant, so that doesn't really do anything but put a constant out front. W is the only variable in this equation. And what W represents is the number of ways we can rearrange the system on a microscopic level, switching particles or whatever you want to do, and it still looks the same macroscopically. So W is the number of ways we can rearrange the system and it still looks the same on a macroscopic level. So how do we interpret the second law of thermodynamics? Well, I mean, higher entropy states where W is bigger, okay, are always more probable. It's more likely that you'll be in a state where W is bigger. So all the second law of thermodynamics is really saying is that systems, if they go from low entropy to high entropy, if entropy increases, all that's happening is the system is going from a state that's less probable to a state that's more probable, okay? All that the second law really says is the system tends to go to the more probable state. That's really all it means. Okay, so we're going to do a quick calculation here, okay? Suppose you have a box with 4 gas particles in it, which are just constantly randomly moving around. What is the probability of finding the system in a state where there are 3 particles on the right side and 1 particle on the left side like this? What is the entropy of that state? Okay, so find the probability of this happening and also calculate the entropy based on the equation I just showed you. Also, look at this case where we have 2 on the left and 2 on the right. What's the probability of this happening? And what's the entropy of that state? So try to work this out. Pause the video for a second and see if you can get it. And by the way, use the analogy of the coin flips. It's pretty much the same idea as the coin flips here. So you can use that to your advantage. So anyway, pause the video, see if you can get this, and then we'll go through it together. So I'm actually going to leave this here on the screen, what we worked out for the 4 coin flips, because the box of gas with 4 molecules is perfectly analogous to this. So let's say we're thinking about the case where we have 3 on the right and 1 on the left. So 3 molecules on the right, 1 molecule on the left in the box of gas. Well, this is like getting 3 heads and 1 tails in a series of 4 coin flips, because if we write down the possible ways, the possible microstates, where you have 3 on the right, 1 on the left, well, you could have RR, RL, so that means the first 3 molecules are on the right and the other is on the left, or you could have RR, LR. That's another way you could arrange the molecules, so there's 3 on the right, 1 on the left. You could have RL, RR, and then you could have LR, RR. So this means the first one is on the left and the other 3 are on the right. So there are 4 ways this can happen. There are 4 microstates that look like this. So W is equal to 4. There are 4 different ways we can rearrange the particles so you still have 3 on the right, 1 on the left. That's what W represents. And again, since this is perfectly analogous to the coin flips, N is 16. That's the total number of microstates that are possible for the system. Just like when you flip a coin 4 times, there are 16 possible ways that can happen. So remember, probability of seeing the gas with 3 on the right, 1 on the left is W divided by N, which is 4 divided by 16. or 1/4. So there's a 1 in 4 chance you'll see 3 on the right, 1 on the left. In terms of the entropy of this state, what would S be? Well, that's given by Boltzmann's constant times natural log W. And so we can calculate this as well. Boltzmann's constant is 1.38, 10 to the minus 23 joules per Kelvin. We multiply this by the natural log of W, which is 4. If you work this out, you get 1.91, 10 to the minus 23 joules per Kelvin. Okay. What about this? 2 on the right, 2 on the left. Okay, so let's think about how many different ways we can have a box of gas with 4 molecules. 2 of them are on the right side, 2 of them are on the left side. Well, that's perfectly analogous to this case where we get a series of 4 coin flips and we have 2 heads, 2 tails. Remember, there were 6 ways that could happen. So W is equal to 6. So what's the probability of this? You'll have W divided by N, which is 6 over 16. So 3 over 8. What's the entropy? KB times natural log W. So we have 1.23, sorry, not 1.23, 1.38, 10 to the minus 23 joules per Kelvin, multiplying natural log 6. So what does that work out to? 2.47, 10 to the minus 23 joules per Kelvin. Guess what? This is higher entropy. Compared to the other state, if we can just compare these two numbers. It's also higher probability. And this is really what I was getting at as far as the second law, how to interpret it in terms of statistical mechanics. Okay? Higher entropy states are more probable. So your system is naturally going to evolve. If it starts off with low entropy, it's going to increase its entropy. Okay, that's why entropy tends to increase, because it's more probable for entropy to increase. That's really the explanation in stat-mech terms. Okay, so I want to take a look at an example where we can actually apply these ideas from stat-mech that we just talked about. And this is a diffusion of a dye. So what you should imagine here is we have a dropper, and we'll take a little drop of food coloring or maybe some sort of dye and drop it into this water. And we know what happens over time. Of course, as time goes on, the dye starts to mix in with the water. So it goes from kind of being all concentrated here, it diffuses out a little bit, and then over time, it becomes more mixed in until the point where it's perfectly evenly mixed with the water. So this is the final state that we expect to see. Now, why is it that this is the progression of things? Why do we end up with this even mix at the end? And the way we can understand this is to think about entropy. Because this final state actually has way, way more microstates. There are far more ways you can arrange all the molecules so that there's an even mix like this, compared to microstates where there's just a concentration of dye here and no dye anywhere else. So many more microstates that look like this compared to microstates that look like this. And so what we're saying is we start off in a low entropy state, okay? And then we end up in a high entropy state. And of course, according to the second law of thermodynamics, we expect entropy to be increasing. So the fact that the dye spreads out is just a consequence of the fact that the entropy of this system is increasing over time. And the reason it doesn't go back and unmix, we don't see this evenly mixed state go back to this state over here. The reason that doesn't happen is because that would involve entropy decreasing, okay? And that would violate the second law of thermodynamics. Okay, so the next example I want to show you deals with thermal equilibrium. And this is something we started talking about at the very beginning of the semester. So the idea being that if we have two objects, one of them is hot, the other is cold, and we allow them to touch, we allow them to make contact, that heat is going to flow from the hot object to the cold object. So if heat is escaping the hot object, its temperature is going down. If heat is flowing into the cold object, its temperature is going up. So at some point, they're going to reach the same temperature. And this is what we call the state of thermal equilibrium. Okay, obviously, once this happens, it's not like we go back to the original state where, again, there's a hot and a cold object. This is a one-way street. So the reason for that is that there are far more microstates where the energy is evenly shared between the two blocks. So remember, if the temperature is equal, that means on average, the energy of the molecules in this block are the same as the average of the energy in this block. So the energy is evenly shared in some sense between the two blocks. Originally, energy is kind of being hogged by the hot block, right? It's more concentrated over here. It's less spread out. So because there are so many more microstates that look like this, where the energy is evenly spread out, compared to microstates that look like this, where it's all kind of concentrated over here, what we say is this is a high entropy state that we end up with, and this is a lower entropy state, the one that we started with. So all that's happening is the system is evolving from a low entropy starting point to a high entropy endpoint, and we know that entropy doesn't decrease, so we don't go back. We don't go back to where we started. Once you reach thermal equilibrium, that's it. You don't go back to the initial state. So this takes us to the modern view of the second law of thermodynamics, okay? So remember what we originally said about the second law of thermodynamics. It's the idea that the total entropy of the universe increases over time. It doesn't decrease. So delta S for the universe is always going to be something positive. It's never going to be something negative, indicating the entropy is going down. But in statistical mechanics, all we can really say is that high entropy states are more probable than low entropy states. They're more likely than low entropy states, okay? So it's not that entropy strictly increases. It's that it's always much more likely for any given system that you're looking at for the entropy to increase. But it's not like it's literally impossible for the entropy to decrease. That can actually happen. It's just very improbable. So the modern way to think about the second law of thermodynamics is not that it holds in some kind of absolute sense, but it holds true in a statistical sense, okay? It can technically be violated, right? You can technically have entropy decrease, but it's extremely unlikely, okay? And by the way, the bigger your system is, the more particles it has, the more unlikely it is to see entropy decrease. So by the time we're talking about ridiculously large systems like the air in the room you're currently sitting in with like 10 to the 20 something particles, it's so improbable that entropy would decrease that you basically don't worry about it. You don't really even think about that happening. But again, there is technically a tiny, tiny probability for any system you're looking at that the entropy could decrease. And so to put that a little bit more clearly, okay, the idea that you can sort of technically violate the second law, but it's just very unlikely, let's think about a box of gas once again as our system. So we know that if we start the system like this, where there is a bunch of molecules on the left side, and there's just a vacuum on the right side, and there's a door here that's closed, so everything is staying on the left side for now. But if we open the door, open this up, and we allow the molecules to start moving into this chamber, well, over time, we know they'll diffuse, and eventually they'll be pretty evenly mixed, okay? However, it's not impossible, just randomly, through random chance, for the molecules to just find themselves in a situation where they all happen to be back here. So this can happen. It's just very, very improbable. And so that means if you were to see that happen, you'd have to wait a really, really long time, a ridiculously long time. In a similar way, the room you're sitting in right now, it's technically possible that all of the air could just randomly go to one side. Okay, and you'd suffocate, right? But don't worry about that happening, because the probability of that is so tiny that it's not even worth thinking about. But this tiny, tiny non-zero probability that, entropy increases, gas molecules spread out, but then if you wait long enough, it can go back to the starting state where everything was on one side. It can go back to that initial low entropy state. That's called a Poincaré recurrence. Okay, that's what we call this. Okay, so there are a few more things I'd like to say. And I want to go a little bit beyond physics 47. Okay, so what we're going to talk about next is a little bit beyond what I expect you to know for physics 47, but it's really interesting, so stay with me. We're going to talk about the heat death of the universe and the arrow of time. Okay, so let's get into the heat death of the universe. So if we really take the second law of thermodynamics seriously, we take it at face value, what it's telling us is that delta S for the universe is positive. So the change in entropy is always positive, i.e., the entropy of the entire universe is always increasing over time. It's never decreasing, it's just continually increasing as time goes on. So it's natural to wonder, is there any endpoint to that? So is there a point where the entropy is increasing and increasing, but then it levels off and it reaches some kind of maximum value? And in fact, some theoretical physicists have worked out that, yes, we can expect that in the distant future, the universe will reach a state of maximum entropy, and what we call that is the heat death of the universe. But don't worry, this is going to happen roughly in about 10 to the 100 power years. If you don't know, the current age of the universe is about 14 billion years, so about 10 to the 10 power years. So this is really, really far off in the distant future. But what does this final state look like? What does it look like when we reach heat death? Well, basically, the universe itself reaches thermal equilibrium, meaning there are no longer temperature differences between different parts of the universe. So there's no delta T between two parts of the universe. Everything is in equilibrium. Everything has the same temperature. Okay, so what that means is the energy of the universe is evenly spread out. And that's not what things look like right now. You have things like stars that have tons of energy, and then you have regions of pretty much empty space in between where there's very low energy. So it's not true that right now energy is evenly spread out, but that's what will happen once we reach heat death. Energy is evenly spread out. And once that is the case, mechanical work of any kind is no longer going to be possible, because if you remember from what we talked about with Carnot engines and things like this, you need a temperature difference. You need two different temperatures to drive a heat engine to do mechanical work. So if everything in the universe just has the same exact temperature, then mechanical work is no longer possible. So definitely, once we reach heat death, you can't have things like living organisms. You can't have any kind of interesting structure like a star or a galaxy. All you have is just a bunch of particles evenly spread out, all with the same temperature, and it's kind of boring. Nothing can really happen after heat death is reached. Okay, so the next thing you might wonder about is, well, how do we actually get here? How do we get to the heat death of the universe? Because right now, the universe looks very different from the way it will look once we reach heat death. So what kinds of things have to happen along the way for us to reach heat death? So the way we'll think about this is by looking at a timeline. Okay, so on this timeline, we have time that has passed since the Big Bang, measured in years. And right now, today, it's been about 10 to the 10 years since the Big Bang. That's how much time has passed. That's how old our universe is. And right now, we're living in what's called the stelliferous era, where if you look out into the night sky, you mostly will see things like stars and galaxies. So the universe is dominated by stars, and those are arranged into galaxies. But the thing about stars is that they don't last forever, okay? Stars eventually die out. And that's fine. New stars can form. New stars are forming all the time in our Milky Way galaxy. New stars are forming all the time in other galaxies. But if you think about what needs to happen for a new star to form, the short story is basically, if you have a cloud of gas, and that's actually what you're seeing here in this picture of a galaxy, it can collapse under its own gravity, and that can form a star. So what you need to form a new star is basically some cloud of gas floating out in a galaxy. And eventually, those clouds of gas are going to be depleted. It's already going to be formed into stars, so there's no new gas to form new stars. Eventually, that's going to be the case. So now star formation stops. We're not forming new stars in the universe. And then all the currently existing stars die out. So at some point, there are no more stars, okay? That's the bottom line. At some point, there are no more stars. And this happens around 10 to the 14 years. So after this, we're living in what's called the degenerate era. I'm not talking about the 1970s. This is what we call the era of the universe, where we're dominated by the remnants of dead stars. Okay, so all that's left over basically is just the remnants of dead stars. Things like white dwarfs, neutron stars, and even black holes. That's really what dominates the universe now. Okay, if we go a little bit further along the timeline, we can expect eventually that the universe is pretty much dominated by black holes. So these things that aren't black holes can be swallowed up by the existing black holes in some amount of time. The thing that dominates the universe is just black holes. And so now we have what's called the black hole era, where the main ingredient in the universe is black holes. And this is around 10 to the 40 to 10 to the 100 years. That's roughly speaking the black hole era. But the thing about black holes is that they don't last forever, okay? Black holes actually can evaporate, okay? And this is not something I'm gonna try to explain right now, but if you're interested, look up Hawking radiation. That describes how a black hole evaporates. And this was discovered by Stephen Hawking. The basic idea is the black hole can eject particles. And when it does that, the black hole gets a little smaller. And if this just happens over time, eventually the black hole will go away, and all that's left are those particles it ejected. For a black hole to evaporate, it takes a really long time. Okay, so something like 10 to the 40 years for small black holes, things that are about the mass of the sun. For the largest black holes in the universe, it's going to take like 10 to the 100 years for those to evaporate. But eventually, the point is, if you wait long enough, all the black holes have evaporated. So what's left? Well, now all that's left are just a bunch of low energy particles that are flying around the universe. That's all that's left. And this is when we reach heat death, okay? The energy is pretty much evenly spread out in these low energy particles. There aren't any structures like stars and galaxies anymore. Nothing really interesting can happen at this point. That's heat death. Okay, once you reach heat death, there's really nothing new that can happen. Okay, so that brings us to the arrow of time, which is the idea that time seems to have a direction associated with it. It seems that time only flows in one direction. That is, if I wait around, eventually it's going to be tomorrow, but I'm never going to be able to go back to yesterday. I can't reverse time and go back to the past. That seems like an obvious thing to say, but physicists are really actually trying to understand why that is. So what is it in the laws of physics that gives time a direction? And this is a harder problem than it looks like, and it's not a settled issue by any means. And the reason this is kind of a hard problem is if you look at most of the laws of physics out there, it looks like they're time symmetric. So what that means is in the laws of physics themselves, there's not really a distinction between the past and the future. There's not a distinction between time going backward and time going forward. So anything in the physical law that can happen one way can also happen in reverse. Most laws of physics are like that, okay? But the second law of thermodynamics appears to be the only exception to that, where it's not time symmetric, okay? In the second law of thermodynamics, there is a difference between the past and the future. Because in the past, entropy was lower. In the future, entropy is higher. So we can actually distinguish between them in the second law. And that actually may be the reason for the arrow of time. It may be that the reason we seem to perceive time going forward is that the entropy of the universe is increasing. Okay? That might be the explanation for the arrow of time. So in other words, as time goes forward, the entropy of the universe increases. That means that early on, very early in the history of the universe, near the Big Bang, we must have started off with very low entropy because entropy has been increasing for billions of years, and it's still increasing today. But then we have this idea that eventually we'll reach heat death, and now entropy is at a maximum. So it's not really increasing anymore, it's just sort of leveled off at some maximum value. At that point, it's actually sensible to ask whether or not time has any meaning. Okay? Is there even a meaning to the direction of time once we reach heat death? So I'm not even going to attempt to answer these questions. These are all completely open questions that modern day physicists are thinking about, but I just wanted to make you aware of them. It's kind of a cool direction you can go in when thinking about the second law of thermodynamics. So with that said, this stuff we just talked about, heat death of the universe and the arrow of time, that's sort of just for fun. Not going to test you on this, but everything else will be fair game. And with that said, this concludes the video. So I'll see you in the next one. And until then, be safe out there, be healthy, take care.